I'll just start my recording. Then share my screen. Somebody, you are able to see my screen, right?
Yes.
Okay. So this session is going to be very interactive. Whether it is right or wrong, whatever you feel, you can just answer. Okay. And if it is wrong or something, I'll just correct it. Okay. So not to worry, it is going to be interactive session and it's going to be learning for both of us. Okay. Okay. I welcome you all for the week 6 live interactive session for the course Polymers, Concepts, Properties, Uses and Sustainability. You're able to see my screen, right? The presentation?
Yes, it is shared.
Okay, fine. Let's get on. So we'll have the brief recap of lectures of week 6. So lectures of week 6 were on physicochemical, mechanical and electrical properties of polymers. Basically the properties of polymers were discussed in detail. So this is in continuation with week 5 lectures which was also related to properties of polymers. Okay. So lecture 38 was on physical and chemical aging. Okay, this was with respect to sustainability aspect. Okay, so the aging of polymers was discussed. So what are the different effects due to which the aging of polymers happens? Like they may be thermal effects or mechanical effects or due to some solvent and oxidation, UV radiation. These may be one or more of the reasons for aging in polymers. And the aging can be broadly classified as chemical and physical aging. Okay, so the examples of aging was discussed where a synthetic polymer degradation was discussed. Also, there was a discussion on degradation of wood. So when it comes to degradation of wood, it can be aerobic, anaerobic, and destruction through microorganism also. So of which this destruction through microorganism is very unique to natural polymers, correct? So they can be broken down into the the basic forms of carbon, oxygen, and hydrogen, right? And they can enter into the biogeochemical cycle, correct? And how do you identify the groups in FTIR and then related to the aging, right? Those were discussed. And then properties change, the how the property change with aging. So there can be for example there was an example cited like gasket. So gasket becomes more stiff, right? Over the usage, or sorry, what happens in case of gasket? Do you remember? There's a increase in modulus. It becomes stiffer and there's an increase in modulus, right? Which is not, you know, uh, a suitable parameter for its functioning, correct? And there can also be, at the same time, there can be in some other materials where the modulus decreases. The structural component, the modulus decrease, which is also a negative aspects in terms of the functionality of the material. So these were discussed. And then what is the accelerated testing and how do you predict that life, with accelerated testing, because we do not have all time to do the entire shelf life study. For example, if a material is going to have a life of 25 years, we cannot study the properties for 25 years. So we do some accelerated testing, right? We give some harsh parameters so that we understand how the life would be under a normal condition, when by doing the by giving some harsh or stronger, subjecting the material to a harsh or stronger condition, and then we develop correlations, right? So these were all discussed. Hello Samruddhi, are you there?
Yes.
Okay. When I go to the presentation mode, I may not be able to see whether you are there or not. So just give some yes or no, or you're not able to understand some response. You just give me so that I
Okay.
know that I'm connected. Okay, because I do not know whether I'm connected. I lost my connection also when I go to the presentation mode. Okay.
Yes.
Next, the lecture 39 was on solution properties. So the overlap concentration, the concept of overlap concentration was discussed, right? The based on the solvent and polymer interaction, right? Below the overlap concentration, it is a dilute solution, right? Where the solvent polymer interaction is more, whereas beyond the overlap concentration, the polymer polymer interaction is much more than the solvent polymer interaction. And then the intrinsic viscosity was discussed, right? Intrinsic viscosity is nothing but when your concentration nearly goes to zero, right? And then the theta temperature and solubility parameters were discussed. And then macromolecular solvent interaction, the macromolecular size, right? These was discussed. And then the orientation and the persistent length and the persistent chain, these concepts were all discussed in the lecture 39, that is solution properties. Next, lecture 40 was on conducting polymers. So the overall electrical conductivity was discussed. How does, there is an electrical conductivity in metals. What causes the conductivity in case of metals, in an electrolytic material. In case of metals, there is a electrical conductivity due to electronic conduction, right? Due to delocalized electron, correct? In case of metals, so there is a movement from valence band to conduction band, and the electrons are free to move. That is how the electrical conductivity happens in case of a metallic materials, correct? Whereas in case of electrolyte, there is a dissociation of ions. So polar solvents leads to dissociation of ions, correct? That is how it happens. And how in conducting polymers, the electrical conduction, the electronic conduction happens, right? These were discussed. And what is an all polymer device? So all polymer device can have a conducting polymer and the dielectric polymer, and in a combination of a base material which is a insulating material, right? Was discussed. And where can it be applied in case in sensors, in actuators, right? So these were all discussed. And what causes a conduction in case of polymers? Again, you have the delocalized electron due to the presence of alternate uh, single and double bond, right? Conjugation, due to conjugation there is an electronic conduction. So you have the delocalized electron due to alternate single and double bond, which is nothing but a conjugation. So that was discussed. And then lecture 41 was on dielectric response. So before actually the dielectric response was discussed, what are the types of responses, for a polymeric material, right? A linear response, non-linear response were discussed. And then what is the complexity of response in case of polymeric materials? For example, the polymers will have a storage component as well as a dissipative component, right? That is it. For example, if you take modulus or if you take dielectric permittivity, there will be real part and an imaginary part, which the imaginary part generally says of dissipation. For example, in case of a uh, modulus, the imaginary part says of the dissipation, whereas the real part of the modulus says on the storage of energy. Next, the dielectric properties where response was discussed in details. What are the response of material to different electromagnetic radiation, and the concept of dielectric spectroscopy was discussed. And dipoles in polymers, the polarization. What are the orientation polarization, molecular relaxation, dipolar relaxation, where the d by relaxation was discussed in detail. And then the lecture 43 was on plasticity. So, the concept of yielding, yield strain, and then strain softening, strain hardening, and what are the models of plasticity, the Eyring model, and then Rampere-Gosgood model. These were all discussed in plasticity, right? So, plasticity means there is some permanent deformation, correct? Correct.
Yes.
Yes. In
Yes.
case of elastic, the deformation can be,
Yes, it
brought
is.
back to original state. With the deformed material can be brought back to original state. Whereas in plasticity, there is a permanent deformation or there is a permanent change in orientation, right? Happens. And then next, the final lecture of the week was on properties of composites, where the size, shape, and types of fillers, different types of fillers, different sizes of fillers that can be used, and how premixed form of filler, the pre-polymer and the filler uh, for are used for ease of processing, and then how the composite properties as a function of the constant fillers or reinforcement changes, like the parallel and series mixing rule and Halpin Tsai model was discussed, and then how the amount, distribution, and orientation of reinforcement plays a vital role in terms of volume fraction of fillers and processing was discussed, and then thermal or electrical conductivity of composites, especially the dilute system, the Maxwell model, how the thermal conductivity, what form the thermal conductivity takes, was discussed. So these are the brief recap of the week 6 lectures. Now let's go on to the practice assignment of week 6. Okay. So you were able to recollect any of these, or were you able to, did you go through any of these lectures?
Honestly, I didn't go through any lectures, but I thought that it will be easy for me to catch if I join the online
Yeah.
lectures,
Okay.
like this live session.
Okay. So at least you got some brief on what were all discussed in the lectures, right?
Yes,
Okay.
I'll be looking at these lectures after this.
Okay. Okay. Now let's go on to the question. So the tensile modulus of a thermosetting polyester resin and a glass fiber are 3 gigapascal and 80 gigapascal respectively. If a tensile stress of 110 megapascal is applied along the fiber direction on a continuous uniaxially aligned glass fiber reinforced thermosetting polyester composite with a fiber content of 60% by volume, then the resulting strain will be dash into 10 power minus 3. So this is a gate question, gate 2022 question. Okay, so are you able to understand the question, Samruddhi? Are you there?
Yes.
So you are able to get anything. So this is for a polymer composite. So there is a composite having a polyester resin and a glass fiber reinforcement. So they have given the tensile modulus of the uh, polyester resin and the glass fiber, and they have given some tensile stress that is being applied to the composite. Okay, they have given also the what is the fiber content by volume. Now they are asking what will be the resulting strain. Okay, uh, so you want to give it a try how to approach this?
Sorry.
Okay, no issues. Oh, no issues. I'll explain you. Maybe you can just put yourself on mute because I get some echo. Okay, yeah. So there is one more person who has joined, I guess. Prashanti. Good evening, Prashanti. Hello, Prashanti. You're able to hear me?
Yeah, I'm from NPTEL team.
Oh, okay. Sorry. Okay.
Yeah.
Okay. Fine. Okay. So uh, let's see what are all given in the question and what is asked. Okay. So first, the tensile modulus of the polyester resin is given. So the polyester resin is having a tensile modulus of 3 gigapascal. Next, the tensile modulus of the glass fiber is given, which is 80 gigapascal. Okay. And the third information that is given is the volume fraction of the the volume percentage of the fiber, from which you can calculate the volume fraction, which is nothing but 60% means 60 by 100, which is nothing but 0.6 is the volume fraction of the fiber. Okay. Now they have also given tensile stress along the length of the fiber, which is sigma is equal to 110 megapascal. Now what they have asked is what will be the strain. So next we have to see how to really approach this question. So so you could just imagine the polymer resin, like this. That is the polymer resin, kind of a rectangular polymer resin, where the fibers are reinforced in a continuous uniaxially aligned glass fibers. So that means the glass fibers are aligned in a particular axis. Okay, you're able to understand, Samruddhi?
Yes.
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 So uniaxially aligned means they are aligned in a particular axis. In a single axis, the glass fibers are aligned. Okay. So, and then the next information what it is given is that the tensile stress is applied along the fiber direction. That means the direction in which the fiber is aligned. So this is the direction in which fiber is aligned. You are able to see my cursor, right? This is the direction in which the fiber is aligned. So in the same direction, the tensile stress is applied. So this is the tensile stress that is applied. Okay. So it is applied, along the fiber direction. So this is another information given. So from this, what is the information we can decipher? So we can also just imagine this as a two systems, right? The blue color rectangle, you can imagine it as a polymer matrix, and the black color can be imagined as a glass fiber. Okay, and there's a alignment. Okay, that means the strain, this total strain. Okay, what happens in this case is that since there is a uniaxial alignment, okay, and the tensile stress is applied along the fiber direction, that means the stress taken up by the matrix and the fibers are different, whereas you will end up with the same strain. Both has to extend to the same level, right? If one extends in one way and the other extends in other way, then there will be a non-uniformity, right? Then the structure is not proper, correct? So they have to take the strain, the total strain of the material should be same, correct? You are able to imagine?
Yes.
Yes, the total strain should be same. That means the stress taken up by the matrix will be different, and the stress taken up by the fiber will be different. So how will the total modulus be? So it will be kind of a series combination, correct? So that means the total modulus of the composite will be modulus of the polymer multiplied by volume fraction of the polymer plus modulus of the fiber into volume fraction of the fiber. So we have the modulus of the polymer, we have the modulus of the fiber, we have the volume fraction of the fiber. Can we find out what is the volume fraction of the polymer? What will be the volume fraction of polymer?
0.4.
Yes. Yes, because there are only two components. If one is 0.6, the other is going to be 0.4 because the total summation will be 1. Okay. Now we have all the parameters. So can we calculate and say what will be the modulus of the composite?
Yes. Wait for a while. 50.4.
Is it? Let's see. It's actually 49.2 gigapascal. 0.4 into 3 plus 0.6 into 80 because the fiber is having higher modulus. And that is the ultimate purpose of the reinforcement, so that the fiber can take up more load and help in giving some mechanical strength to the material. Okay. Now can we find out what is
Okay.
the strain in the material? So we have the stress, total stress we know it is 110 megapascal, and the total modulus of the composite we know, which is nothing but 49.2 into 10 power 3 megapascal. So can we find out what will be the strain in the material? Can we? Hello, Samruddhi, are you there?
Yes, I'm there.
Yeah. Can we find out what is the strain in the
We can,
material? Yeah. How?
yes, we can find out from the modulus.
Yes, modulus we have, stress we have. So how do you find the strain?
Stress upon strain
Stre
equals to modulus. So strain equals to modulus into stress.
is it modulus into stress?
नहीं, stress upon modulus.
Yes, yes. Hooke's law we are going to apply. So it is strain is sigma by the total modulus of the composite. Okay. So which is nothing but 110 by 49.2 into 10 power 3. You will end up with 2.2 into 10 power minus 3. That means the value is 2.2 into 10 power minus 3. That is the total strain taken up by the composite. And individual strain is also equal. That is the glass fiber will also get extended by 2.23 into 10 power minus 3. And similarly, your uh, polymer matrix will also take up a strain of 2.22 into 10 power minus 3. Okay.
Why both will get same strain?
That is what is, see, that is what is the one I explained you in the beginning. So what happens is that since this is a uniaxially aligned system, okay, so what happens is that both the matrix and the fiber, should take up the same strain. Okay, it is kind of a series arrangement, one over the other. You would have seen the series and parallel resistors arrangement, right?
Yes, yes,
Yes, the same concept. Here it is a series arrangement. That is why, what you do is that there is an addition of the modulus, right? If there is a parallel arrangement, then it will be 1 by EC is equal to 1 by EP into
yes,
5P. That way it goes, right?
mm, yes,
You are able to remember the resistor concepts,
yes,
parallel and series arrangement. Here it is a series arrangement.
yes,
So if both together, if they are, see, for example, just imagine my this pen. Okay, if both together, so this is having the polymer and the reinforcement. If both together extend to the same extent only, it is actually structurally it maintains its structure. Okay, so that means both will get strained to the same extent. You are able to understand now.
yes.
Let's go on to the next question. And in fact, if you look into this question, the ultimate purpose, you could also see that your modulus of the tensile modulus of the glass fiber is higher. So that means it would take up more load compared to your actual polymer. So this is actually a mechanical reinforcement that is being done to the thermoset polymer. Okay. Now let's move on to the next question. The volume resistivity of a polymeric material is 10 power 7 ohm meter. Find the resistance in mega ohms of a cube of a material of side 1 centimeter. The direction of current flow is as shown in the figure below. This is again a GATE question, GATE 2014 question. So they have given resistivity of a polymeric material, okay, and they have given the dimensions of the material. It is a cubic material with the side of 1 centimeter. Now we have to find out what is the resistance of the material. So can you find out how the resistance would be?
K by resistance.
Which one?
It depends on it inversely depend on resistance.
No, the question is they have given the resistivity, they have given the dimensions. So now we have to find what is the resistance. How do you find the resistance? There is a relationship between resistance and resistivity and the dimensions of the material. With that, you can figure out what is it. And this is actually a basic electrical concept. It's not even a polymeric concept. You are able to recollect something? Samriddhi, you are able to recollect something?
Yes, resistance equals to resistivity into
Okay.
length upon area.
Yes. Yes. Can you just calculate and say what is the resistance of the material, of this cubic material?
Yes, yes. 10 to the power 7.
Hmm?
10 to the power 7.
Is it 10 to the power 7? You have to note down one more thing in the question. Then your value will change. What is it you're missing?
Ten to the power 5. 4.
Is it 10 to power 4? Why is it 10 to power 4?
Units are different.
Okay, units are different. So you said your resistance is resistivity into length by area, correct?
Yes.
Now you just calculate and say. Okay, yeah, calculate and say. You found out it is correct. The units are different, so you have to bring in the unit consistency. How much it goes to.
It will be 10 to the power 1.
Is it? Anyway, we'll just see how the solution is. So they have given the volume resistivity rho, which is nothing but 10 power 7 ohm meter. Next, what is the resistance is the question. So given a cubic material of side 1 centimeter. That means when you convert centimeter to meter, it is 0.01 meter, right? Yes. Right. 1 centimeter is 10 power minus 2 meter, which is nothing but 0.01. Correct. So now resistance is rho L by A. So 10 power 7 into length is 0.01. Divided by area is 0.01 into 0.01. That means 10 power 9 ohms. Right. So they have also asked one more thing. What is the resistance in mega ohms? So 10 power 9 ohms means, so ohms to mega ohms. So just divide by 10 power 6, you will get 1000 mega ohms. Right? 10 power 6 ohms is equal to 1 mega ohm. So 1000 mega ohms is nothing but 10 power 9 ohms. So that means the resistance of the material is 1000 mega ohms. You are able to understand?
Yes.
Now let's proceed. Okay. So based on the solubility parameter, the best solvent for polyethylene is, the solubility parameter for polyethylene is 6.2 megapascal power half. So which is the best solvent? This is based on GATE 2009. So they have given four options. One is tetrahydrofuran, for which the solubility parameter is 20.3 megapascal power half. The option D is toluene, which is 18.3 megapascal power half. Then third one is acetone, which is 19.9 megapascal power half. And the last one is methanol, which is 29.7 megapascal power half. Which of these is the best solvent? Considering the solubility parameter of the polymer polyethylene and the solvents. You are able to get any idea?
No.
Okay, let's proceed with the answer. The actual answer is toluene with a solubility parameter of 18 power 3 megapascal power half. So, the best solvent for a polymer is the solvent which has a solubility parameter very close to that of the polymer. Okay, so they have given the solubility parameter of polyethylene, which is 16.2. Now they have also given for all these solvents what is the solubility parameters. For example, for tetrahydrofuran it is 20.3, toluene it is 18.3, acetone it is 19.9, and methanol it is 29.7. So among these, which solubility parameter is very close to polyethylene? So if we compare the four options and the solubility parameter of the polyethylene, then we could see that toluene is having the very close solubility parameter to that of polyethylene. So among the given solvent, toluene is the uh, best solvent. Okay.
Okay.
Okay. to understand. So the solubility parameter, when you compare, it should be very close to that of the polymer. So the closer the solubility parameter between the polymer and the solvent, the more, uh, the polymer can be dissolved in the solvent in a better way. And the solvent is the best solvent, and the polymer can take more of an extended conformation. Okay, and the solvent and polymer interaction will be much more. Okay.
Yes, ma'am. Is the solubility parameter are available, or we have to call calculate?
These will be available. There will be a database in from which you
Okay.
can get the solubility parameter. They can, they can also be calculated. Uh, if one is given from that, there will be some empirical correlation from which you can also identify. But there will be databases where you can get the solubility parameter. Okay.
Okay.
Yeah. So for a problem statement given, they may give solubility parameter of the one, and they'll say that it is the best solvent, and they'll give some empirical correlation from which you can also calculate the other. Okay.
Okay.
Next question. Identify the physical aging process in a polymer among the following. So they've given four options. So from which you have to identify which are the physical aging process. Okay. So they've given crystallization, oxidation, phase separation, cross-linking, and chain scission. So from this, we have to identify which are the physical aging process in a polymer. What leads to physical aging?
Crystallization, phase separation,
Okay, only those two.
and chain scission.
Is it
Maybe.
is it
I'm
chain
not sure.
scission? Okay, you're saying maybe. So you were actually right in the beginning. It is crystallization and phase separation only. Because in oxidation, cross-linking and all, no, some chemical reaction is happening, and similarly in chain scission, the chain gets cut. Scission means cutting. So that means there must be some kind of a chemical change that is happening so that the chain gets cut. Right? So only crystallization and phase separation are the physical processes. For physical aging. Okay. Okay. Now next, let's go on to the next question. The persistent length of polyethylene is 0.7 nanometer, while that of double-stranded DNA is 30 to 80 nanometer. This implies that polyethylene is dash than double-stranded DNA. So what information you can get from the persistent length? They have given the persistent length of the polyethylene and persistent length of the DNA. Any thoughts?
Elastic.
No. There is something else you can decipher. What else can be?
Size related, we can say. Yeah. It can be coiled more.
Coil.
Polyethylene.
Uh, okay. So shall I just go ahead with what, or you want to give one more thought?
You can
Or
say.
maybe I'll just give a clue. So it is more related to the flexibility, whether the polymer is
This
flexible or rigid.
particular term, it is flexible.
Which is flexible?
Polyethylene.
Okay, why do you say it is flexible?
Because its persistence length is lesser even than DNA.
Yes, yes, yes. So the polyethylene is more flexible than double stranded DNA. So you can see that, there's a relation between the orientation correlation, the persistent length relation, right? So as a persistent length is lower, there's a lesser orientation correlation. Whereas when the persistent length becomes infinity, then the orientation correlation increases. So that means, the persistent length is of the order of contour length. That means your the rigidity is more, right? It becomes more of a rigid. Whereas if it is in a more flexible system, the orientation, correlation is lesser also, right? So the lesser the persistent length, the lower is the orientation correlation, right? And also your polymer flexibility is higher because the chain is more flexible. Okay,
Yes.
now let's go on to next question. Electrical conductivity of a doped polyaniline is dash Siemens per meter. Is it 10 power 7 or 10 power 14 to 10 power 16? Or is it 10 power minus 14 to 10 power minus 16? Or is it 10 power minus 2 to 10 power 4? Among these, in which range the polyaniline electrical conductivity would be?
I don't know.
Okay, it's actually 10 power minus 2 to 10 power 4. It is in the semiconductor range. So polyaniline is nothing but a polymer. So it is having conjugation, and doped polyaniline, it actually, doping actually helps in, making the polymer
Conduction.
becoming conducting. Though, helps in delocalization. Okay. And the delocalized electrons to start moving and creating a conductivity. Okay. So this is of the semiconductor range. So it is between 10 power minus 2 to 10 power 4. Okay. So when, for example, for a highly conducting material, the conductivity would be of 10 power 14 to 10 power 16. Whereas insulators, it will be in, 10 power minus 14 to 10 power minus 16. So very low. Okay. Sorry, conducting material, it will be of the order of
Okay.
10 power 7. Okay, next. Chemical aging by photooxidation leads to conversion of CC bond in natural rubber to what happens due to photooxidation? What happens to the CC bond of natural rubber uh, due to photooxidation? Does it get converted to CH bond, or does it get converted to COH bond, or does it get converted to COOH bond, or does it get converted to CO bond? What happens during a photo oxidation process? This was actually discussed in the lecture.
It's CH bond.
Is it CH-CH bond? Does it get converted to CH-CH bond? There is one more clue in the question. There is a chemical aging by some process. You want to take a guess again?
It may be B then. COH. I'm not sure.
Okay. It's actually C double bond O bond. Okay. So if you look into the
Okay.
isoprene unit, it is actually, this is the isoprene unit. Due to photooxidation or ozonolysis, what happens is that this CH2, CH3, this CC bond gets converted to C double bond O bond. Okay, this is what happens. So in case of a natural rubber. Okay, now let's go on to next question. So a sample of natural rubber cis 1,4 polyisoprene is vulcanized such that one of every 240 chain carbon atoms are cross-linked. The formula unit of isoprene monomer is C5H8 and the molecular weight of that unit is 68 gram per mole. The average molecular weight rounded off to the nearest integer between the crosslinks is dash. So this is again a GATE question, GATE 2021 question. So what have they given? They've given vulcanized natural rubber, and they've also given that there are 240 carbon atoms between crosslinks. So vulcanization causes cross-linking of natural rubber. You know that, right? Hello?
Yes, yes.
Yeah. So now they have given that there are 240 carbon atoms in the chain between two crosslinks. Now we have to, and they have also given what is the formula unit of isoprene and the molecular weight of the isoprene unit. Now we have to find what is the average molecular weight between the crosslinks. So how do you do that? Any thoughts? Any thoughts?
No, ma'am.
Okay. Let's proceed how to solve this. So they have given natural rubber cis 1,4 polyisoprene, and they have given the molecular weight of isoprene monomer C5H8 is 68 gram per. Next, they have given carbon atoms between crosslink, which is 240. Okay. Now, if you look into the isoprene unit, so how many carbon atoms it is having between a for a single isoprene monomer? If you look into the this is the isoprene monomer, okay, and this is the natural rubber structure. So if you see along the chain, there are four carbon atoms, correct? There is a CH2, CH, double bond CH, CH2, and there is a side group of CH3. So that means there are four carbon atoms in the single isoprene unit in natural rubber. Okay, this gets polymerized. Okay, so what happens now? They have given 240 carbon atoms, and number of carbon atoms on backbone per isoprene unit is 4 carbon atoms. So from this, how many isoprene unit is present between two crosslinks can be identified, correct? How do you identify that? How many isoprenes are between two crosslinks?
240 divided by 4.
Yes, perfect. So number of
60.
isoprene units is, yes, 240 per crosslink is 240 by 4, which is 60 units. So from this, can we find out what will be the average molecular weight of this, uh, you know, uh, uh, you know, polyisoprene between crosslink? Can we find out?
Yes.
How do you find out? How do you find out the average molecular weight between the crosslinks?
From Avogadro number, they have to calculate.
No. The answer is very simple and straightforward. Just
16 to
think.
68.
Yes, yes, you're right. So you have the number of isoprene units per crosslink, which is 60, and we know the monomer molecular weight, which is 68. So just multiply that. So that will give you the average molecular weight between the crosslinks. So 60 into 68, just nothing but 4080 gram per. Okay. So let's go on to the next question. Flexible PVC tubes are used for watering. If some organic solvents are passed through these tubes, it becomes stiff. This is due to the fact that the organic solvents, pla- plasticize PVC and raise TG, or remove the plasticizer and raise TG, or remove the plasticizer and lower the TG, or it reacts with PVC and increase the TG. What does it cause? So this is a GATE 2018 question. What happens, when some organic solvent is passed through the tube, the PVC tubes become stiff. What is actually happening in that case?
Plasticize PVC.
Does it plasticize PVC? The material becomes stiff. That is a clue here. So what might be the possible thing that is happening due to this organic solvent if we pass organic solvent instead of water in PVC tubes? Just give a thought.
Plasticize PVC, I think.
Okay, it is actually, it removes the plasticizer. Okay, so PVC is,
Plasticizers are used to make the PVC tubes rigid.
no, plasticizer, it helps in improving the flexibility of the material. It plasticizes, so the material becomes more, flexible. Okay, and it raises the TG. So what happens is that generally PVC tubes, PVC is a rigid polymer. Okay, they add plasticizer to make it much more flexible, and then they use it. They make tubes for watering. But if instead of water, if you use some organic solvents, these organic solvents, what they do is that they remove the plasticizer present in the PVC, making it more stiff, and also they raise the TG. Okay, so this is the option. Okay. The next question is, the correct statement with respect to electrical property of polymeric materials is option A. For non-polar materials, dielectric constant is independent of frequency and temperature. For polar materials, dielectric constant depends on frequency but not on temperature. For non-polar materials, power losses are high and depends on temperature and frequency. And the last option is for polar materials, power losses are low and independent of frequency. Which of these is the correct statement with respect to electrical properties of polymeric materials?
It can be B.
Polar materials dielectric constant depends on frequency but not on temperature, is it? Okay, why do you say so?
Because for polar material, dielectric constant is much related concept. In non-polar material, dielectric constant is not present.
Okay, you feel that option. Actually, the answer is for non-polar materials, dielectric constant is independent of frequency and temperature. Option B is not correct because, see, for polar materials, dielectric constant depends on frequency as well as on temperature also. Okay, because temperature also affects the polarization. Similarly, the frequency, okay, the time scales, okay. Whereas in case of non-polar materials, there may be some residual dielectric behavior, which really doesn't depend on the frequency or temperature. So that is why, for non-polar materials, dielectric constant is independent of frequency and temperature. That is the only correct statement. Whereas the remaining are not correct statements. Okay. Next question. Dielectric permittivity can be obtained from dash component of electric field and electric displacement. Any thoughts? I think maybe difficult for you because you didn't go through the lectures, right?
Yes.
It is actually in phase component. Okay, when you apply a sinusoidal wave to electric field and electric displacement, when you apply a sinusoidal wave, either changing the electric field and observing the electric displacement, or vice versa, when electric field and displacement are in phase, then you will get the dielectric permittivity, and out of phase will give you the dielectric loss of the material. Okay. So because for polymeric materials or viscoelastic materials, it is actually the complex permittivity. So it will have a real component and the imaginary component, where the real component which says the dielectric permittivity or the capacitive behavior, whereas the or how it stores the electric energy, whereas your out of phase component, it says on the uh, dielectric losses. Okay. Now the next question is, nonlinear response is characterized by dash between the input and the material. Any thoughts?
No.
Okay, no worries. So there is a larger interactions actually between the input parameter and the material, because there will be a significant changes in the material structure. Whereas in linear response, we are just playing with the equilibrium only. So the material just moves away from one equilibrium state to another equilibrium state and then comes back. When the the input parameter, whether it is a load, stress or strain, okay, or electric field, anything is applied, it just moves away from the equilibrium and comes back in case of a linear response. Whereas in non-linear response, there will be a significant changes in the microstructure. Okay. And there are larger interactions between the input parameter and the material response. Okay. Next exam. Yeah, you were you have any doubt? You were about to ask something.
No.
Okay. So examples of practical phenomena of non-linear response includes, what are the practical phenomena where non-linear response can be observed. So just now we discussed that in case of a linear response, it is just moving away from equilibrium and then just comes back. Whereas in non-linear response, there's a larger changes or significant changes in the microstructure. So which are some of the examples where there are significant changes in the microstructure?
Rheological properties, we can say.
Is it rheological properties? Again, in rheological properties, you will have linear response and
Pseudoplasticity.
huh?
Pseudoplasticity.
Yeah, semi-plasticity. Somewhere you are saying, but not exactly. It is actually, as you said, plasticity. That means plasticity means there is an yielding. So yield is an example where the response becomes non-linear because there is a significant microstructural changes or there is a permanent deformation. Similarly, in case of
Yes.
fracture also, the material breaks down. That means there is no more small changes, but there is a significant change. That means the material literally breaks down. And similarly, in case of electrical response, there is an electrical breakdown. These are some of the examples where non-linear response happens. That means there is a significant changes in the material structure that is happening. Okay.
Okay.
Yeah. So you said semi-plasticity, it is more of plasticity. That means yielding. Okay, the plastic response is, leads to a non-linear response. That means there is some significant change in the material structure. Correct?
Yes.
Yes. Okay, now let's go on to the next question. Scaled response and superpositions are features of nonlinear response. Is it correct? Is the statement correct? Scaled response and superpositions.
I don't have idea.
Okay, it is actually wrong. The scaled response and superpositions are features of linear response. So, for example, in case of linear response only, you can do the scaling. For example, say for example, you have an electrical property. You're passing a current and you're finding the voltage. Okay, and then you're passing some other current and you're finding another voltage. Now, if you pass the sum of these currents, for example, 1 ampere in one case, the second case you apply 2 amperes. For example, when you apply 3 amperes together, and for example, when you apply 1 ampere, you get 1 volt. Okay, and you apply 2 amperes and you get 4 volts. Okay, so now, for example, if you apply 3 amperes, what will be the potential difference, or what will be the voltage? If the question, if you think about that, okay, if if it is in the linear response regime, if the applied input or if the applied current is in the linear response, that is a small perturbation only, what happens is that you can directly find out the what will be the possible output of voltage for a 3 ampere current. For example, in 1 ampere I said 1 volt, for 2 amperes I said 4 volt. So if I apply 3 amperes, the if it is going to be a linear response, then I can scale from the first and second response, that is 1 plus 4, which is nothing but 5 volt will be the possible voltage or potential difference which can be obtained from the sum of the first two responses. Okay, and similarly your time temperature superpositions and all, for example, instead of doing for 100 hours together, if you do it at a higher temperature, like instead of 25 degrees you do it at 100 hours, you get some response of the material, you get some modulus of the material. Okay, instead of doing for 100 hours, if you cannot afford for 100 hours, but you can do it at a by applying some small amount of strain for 100 hours, what is the stress response, so that you can actually identify by doing it at 40 degrees for for a much shorter time. So that kind of a superposition, you can do the superposition only if the response is linear, only if your perturbation is going to be very small and it is in the linear response regime, you can do the scaling and superposition. Okay, you are able to understand?
Yes.
Yes. Okay, now let's go on to the next question. Match the processes with the response of the material. Atomic polarization associated with vibration modes of atoms. B is molecular relaxation, which is associated with translation, rotation, and vibratory modes of bonds or molecules. And then electronic polarization associated with electronic relaxation process. So, which of these processes happens and what are their corresponding responses would be? Conducting response, optical response, mechanical and dielectric response in each of these polarization process. You have to match.
A for white, conducting response.
Hmm?
Atomic polarization for conducting response.
Is it conducting response? Give a thought. There are three different types of polarization discussed here. One is atomic, next is molecular, and third one is electronic polarization. Any thoughts? Any thoughts? Anything you want to give a try?
No. Electronic polarization for conducting response.
Electronic polarization. Yes, you are right. Electronic polarization is for the conducting response. Okay. The other two are atomic polarization. It is associated with vibratory mode of atoms.
Optical.
So this is related to the optical response of the material. Molecular relaxation. It is again, associated with much larger dimensions, right? That means your translation, rotation, and vibratory modes of bonds or molecules. So this plays a role in identifying the mechanical and dielectric response of the material. And finally, electronic polarization, as you said, as it is associated with electronic, relaxation. That means electronic relaxation means the electrons, you can correlate with the conducting response of the material, right? The electrons are gets relaxed and it's free to move, so you can get the conducting response of the material, whether it is really relaxing to a greater extent to give a conducting response or not. Okay, now let's move on to the next question. The dipole in PVC is on dash, while in polyethylene oxide it is along dash. Where do you get? So PVC and polyethylene oxide are they form dipoles. Okay, uh, whereas they have their dipoles forming groups in different positions. So where is it in case of polyvinyl chloride and where is it in case of polyethylene oxide? If you know the structure, you can find out. They can show some polarity because of some groups present in them. What are the groups and where are they present? Samruddhi, are you there?
Yes.
You are able to think anything? Polyvinyl chloride and polyethylene oxide.
Yes. Both have different groups in different direction. Like in PVC, it's branch, and for PEO, it's linear.
Huh? It is in?
It, it is within the chain.
Okay, okay, you're right. Yes. So it is actually in case of PVC, it is the side group, not the, it's the branch. It's actually the side group. Okay. Uh,
Yes.
uh, so technically you can say it as a branch if you have a whole different group or something, or some, extended chains are there. Here it is just a small side group present. So here this chlorine in the side group, this portion can polarize because, chlorine can become more negative, so it can attract electron and gets polarized as a negative group, and here it becomes a positive. Okay, and similarly in polyethylene oxide, oxygen is present in the backbone, so this helps in causing a polarity. Okay, yeah, you are right. Now next question. In Debye relaxation model, the angular frequency tends to 0. That means the dielectric permittivity tends to dash, and the dielectric loss epsilon double prime is proportional to dash. What happens in case of a Debye relaxation model? when the angular frequency tends to 0. I think you want to give a thought? Anything you are able to recollect or
It tends to zero.
tends to 0? No?
It is in linear proportion with omega. So
No. Actually, if you know the model equation, you can find out what happens to the dielectric permittivity and dielectric loss. Just hold on a moment. I'll just switch on the light and come. Yeah. What happens?
I couldn't guess.
Okay. Let me proceed. The answer is that it is actually epsilon per, tends to epsilon s. Okay. Uh, it becomes perfectly dielectric, or the dominant permittivity comes into picture. Okay. In case of a uh, when the frequency, when the frequency, angular frequency is very low, when the applied frequency is at very low frequencies, so it becomes more of a dielectric material. And what happens to the dielectric loss is that it becomes proportional to omega. Okay. This is what is the actually the equation. So when you, so this is some this is the dominant polarization or the dominant permittivity, okay, epsilon s, and this is some residual polarization, okay, and this is the complex permittivity equation for a d by relaxation process. So when omega tends to 0, what happens? So when you substitute 0 for this, then you will get this term goes to 0. So it is just epsilon infinity plus epsilon s minus epsilon infinity by 1, which is nothing but epsilon infinity plus epsilon s minus epsilon infinity. That means your epsilon prime is equal to epsilon s. And similarly, when you apply omega is equal to 0 in this case, so in the denominator, then again here, epsilon double prime will be function of omega only. It becomes just proportional to omega at very low frequencies. Okay. So this is how, the curve looks with, with respect to omega, your E prime and E double prime. So your E prime at very low frequencies, it becomes a dominant polarization, that is epsilon s. Okay. And your omega becomes a function of sorry, your epsilon double prime becomes a function of omega alone. Okay. You're able to get it?
Yes.
Okay. Okay. Next question. When a woven fabric is reinforced in the polymer, the properties are similar along the plane while different along the thickness direction. This nature is referred to as dash. So there will be, when there is an woven fabric which is reinforced in a polymer, the properties will be isotropic along the plane. Whereas in the thickness direction, the properties are different. So this nature, what is this nature called?
Anisotropic.
Anisotropy along the thickness direction. Okay, but there's a specific terminology. If you're able to think about it, there is an anisotropy in the behavior. Along the plane, there is one behavior, and along the thickness direction, there is another behavior. So, what is this actually called in specific? This is actually called as transversely isotropic. Along the transverse direction, the properties are same, so it is transversely isotropic. Okay, along the x and y direction. Whereas in the z direction, as you said, there is an anisotropy, or there is a difference in behavior. So this phenomena is called as, or along the longitudinal direction, there is a difference in behavior. That means it is transversely isotropic. Okay, because of the
Okay.
anisotropy in the longitudinal direction. Okay,
Yes.
now next. Dash of reinforcement or fillers leads to orders of magnitude increase in property. For example, you have electrical conductivity of a system having certain amount of fillers. Okay, and at a particular amount of fillers, this electrical conductivity increases by orders of magnitude. For example, if it is like in 10 power minus 2, the electrical conductivity, it becomes 10 power 3 or 10 power 4. That means there is 6 order increase, right? So what causes this order increase? When the amount of fillers is changed. Any thoughts?
Which properties they are talking about?
Any property for a polymer composite, when the amount of fillers are changed, okay, something happens to the polymer, polymer composite, and this leads to orders of increase in magnitude of some properties. Any property for that matters, there will be an order of increase, orders of increase. What is this phenomenon called? Something happens to the fillers in the matrix, in the polymer. Some phenomena happens to the fillers that leads to increase in properties by order of magnitude, or by orders of magnitude. You want to give a thought?
Hmm.
Okay, this is actually when percolation of the reinforcement or fillers happens. So if you just look into this, see, for example, this is some polymer matrix where some fillers are present, fillers or reinforcement are present. So as you keep on increasing the fillers or reinforcement, the amount of fillers or reinforcement at some particular concentration, what happens is that there will be some connection happening between these fillers. Okay, see, if you could see here, these two fillers are connected. Similarly, these fillers are all getting connected. Right here, there is a connection, complete connection. Correct? So there's a percolation happening. This connection is called as percolation. So they form a percolated network or connected network. Uh, so as you increase the amount of fillers, amount and distribution of fillers also. Okay. So as you increase the amount of fillers, depending on its distribution and orientation of fillers also plays a role, so that it forms, a connected network. And this phenomenon is called as percolation. So once percolation happens, there will be, orders of increase in magnet, properties. For example, if you could see, sigma is the current conductivity and phi f is the volume fraction of the filler. So as you increase the volume fraction of the filler at particular concentration, you could see that there will be some orders of magnitude, nearly 7 to 12 orders magnitude increase in the conductivity once this network gets percolated. Okay. Hello.
Yes.
Yeah, once it gets forms a percolated network or a connected network, the properties becomes, multiple fold increased once this percolation happens. This again depends on what type of fillers, and then the amount of fillers, how the fillers are distributed, and then, orientation of fillers also. For example, the quantity, the volume fraction to be added, if the orientation is, in particular orientation, then the quantity might be different. If there is a different orientation, then the quantity of fillers required to form a percolated network will be different when there is a different orientation. The same filler, if the orientation differs also, no, the quantity of filler to be added for a particular percolated network to form will be different. Okay. Okay. Now let's go on to the next question. Yielding leads to a process which dash energy leading to permanent deformation. So, what does yielding cause? That leads to permanent deformation. Yielding is a plastic phenomena, correct?
Yes.
So, what happens to the energy in that case? Does it get stored or does it get lost? Or there will be no change with respect to energy? What happens?
Energy become less.
Okay, that means there is a loss of energy or dissipation of energy, right? So, as you said,
Yes.
it dissipates. So, there will be dissipation of energy because in case of yielding, what happens is that there is a permanent change in the structure. So there's a change from one kind of a material structure to the another form. So in this change from one form to another, there will be some absorption of energy to change from one form to another. So since the change is permanent, the energy is utilized in this changing process, conversion process, and that is why there is a loss or dissipation of energy. Okay. Now next, D by relaxation on cold hole plot is, what is the shape of the plot? Cold hole plot in D by relaxation process. Any idea?
Semicircle or arc.
Yes, perfect. You're right, it is semicircle. So, uh, so if you plot, your E double prime versus E prime, that is a cold plot, it will be semicircle. Okay. And actually for realistic materials, it will be multiple semicircles due to multiple relaxation process that is happening. Okay. So you could see multiple semicircles, right? So that will also end up, if you just connect it, you will get a big semicircle. So this multiple semicircles are due to of cold plot is due to multiple relaxation process happening in the macromolecular system because of its macromolecular nature. Okay. Yeah. The next question. Macromolecular orientation and creation of polymer microfiber surrounded by voids leading to whitening of sample is called dash. Is it shear banding, or is it cold drawing, or is it necking, or is it crazing? What is this phenomenon called? Where macromolecular orientation and creation of polymer microfiber surrounded by voids happens leading to whitening of sample.
I don't have idea.
It's actually called as a crazing process. Okay. Uh, the last question. Plasticity model based on the concept of energy barrier for conformational changes. So the answer for the question, plasticity model based on the concept of energy barrier for conformational changes, Eyring model. And this is the model where there is a hypothesis that there is an energy barrier for undergoing conformational or orientational change. And the measure of this energy is based on the product of stress and activation volume for conformational or orientational change to occur. And in addition to that, for the previous question, where the macromolecular orientation and creation of polymer microfibers surrounded by voids leading to whitening of sample, which is nothing but crazing. A typical class example in real life situation is that when you observe this polythene bags, these transparent polythene covers, when you just pull it out and stretch it, you would see that when it is getting stretched, it also starts to become, the transparent bag starts to become translucent and it starts whitening out. This is the classic real life example where you could see visually see the crazing process happening. Thank you.